Well, good evening, it's Charlie ZL2CTM. Just been spending the last day or so just sort of playing around with the MPF102, the JFET. Just, I guess, sort of starting the idea of looking at sort of low noise amplifiers and just sort of what's out there, and I guess just to get a bit of a better understanding of how they work. It's something which I haven't really used before, so it was certainly been quite interesting. At some point I would like to look to replace the RF amplifier on the SSB rig, that antenna amplifier coming in. So up on that sort of 14, say again, or 14 megs or the 20 meter band, having an amplifier there. Certainly not being used at the moment for the lower frequencies, i.e. the 40 and the 80 meter band. Anyway, so just been sort of looking around, and if you look around on the line and in various textbooks, this is a very common circuit. It's a common gate, so the gate is common to both the input and the output of the amplifier. It's known to be supposedly quite stable, and also has a well-defined input resistance, which we'll look at in a sec. The gain of this is roughly sort of 10 to 12 dB. But why? So I looked at this and I sort of looked at the calculations. I didn't take it any further because they talk about the gain of this really comes about because the input and the output is tuned. So we've got the capacitor here sitting across the secondary of the input transformer T1. So that's a parallel resonance circuit, and then picking off our desired pick off there to match the input resistance of our JFET there. And again on the output, this point here is at RF earth through the 100 nanofarad capacitor, so therefore on the other side of this coil here we have the main tuning capacitor here. So effectively it's across this coil here, because this point here is at earth and that point there is at earth, RF earth there, so it's across effectively. And they talk about that the T1, the T2 are identical, and either a T50-2 for less than 20 meters, and the T50-6 for that sort of 20 meters to 6 meters. Now Rn, incidentally, for this configuration here is 1 over Gm, which is the common source transconductance. And we'll, again, so I keep popping around, we'll look at the formula for transconductance later on. Now, of what's interest, in order to calculate the transconductance here, in order to work out a number of things, as well as our gain and our signal current that's passing through our device here, we need to know two values, something called an Idss, which is the current through the device with 0 voltage on the gate, and something called Vp, our pinch-off voltage. So the negative voltage on this particular JFET here, depletion mode in-channel JFET, what is the negative voltage that is applied to the gate there in order to pinch off, in other words, to turn off that device. And what I mean by that is, if we just look up here on the screen, we can see, courtesy of the internet, an in-channel JFET operation. So this is in our particular case, it's the MPF102, and we can see here that in the normal configuration with 0 voltage on the gate, we have a channel which is at its widest point, so to speak, and current can pass through when there is a potential difference between the drain and the source. In other words, we have a battery of some sort. And as we apply more and more of a negative voltage because it's a voltage controlled device as opposed to a BJT, which is a current controlled device, as we apply more negative voltage, now this side is connected to this side, it causes that depletion zone there to increase and starts to restrict or constrict, more the point, our in-channel through there, and our resistance increases and therefore our current decreases. And if you apply a sufficient amount of negative voltage here, you can actually fully pinch it off and you'll no longer get current through the device. Now if you were to look at the spec sheet for the MPF102, you get quite a range The IDSS here is got a range of 2 to 20 milliamps, and our VGS, which is also known as our pinch-off voltage, ranges there between minus 0.5 and minus 7.5. Now Wes Hayward, WZZOI, says that really in order to design an amplifier circuit, you really can't use a range such as these to make your calculations. You've basically got to put into a circuit, a test circuit, and plot those values yourself, which I've done over here, and which I'm going to cover in a sec. And it's a pretty straightforward and very easy process. So all we have to do is we get our JFET, we put a 100 ohm resistor in the drain, going up to, in my particular case, this amplifier will be looking at 13.8 volts. We have our unknown resistor here, R. This is a variable resistor. I'll be using a switch box there for that resistance, and then we can also measure the current and the voltage. So we measure our current in order to get us ultimately our IDSS, as well as to do our plotting, and our voltage across here gives us our pinch-off voltage. Note here we've got the gate grounded, so as current passes through resistance R here, we get negative on this side and positive on this side in terms of a voltage drop. So that intends, because our gate is sitting at earth, as the source becomes more and more positive, effectively you're driving the gate more and more negative. So in terms of the picture we saw before of how a JFET operates, that's exactly how it does it. The sort of self-biasing here with a resistor in the source circuit. So what I'm going to do over here, I'll just sort of quickly jump across to here. So this is exactly what the configuration we have here at the moment. We've got our JFET here, we've got our 100 ohm resistor, and we've got 2 meters. We've got 1 meter which is measuring, let me just reset that before it times out. We've got 1 meter here which is measuring the voltage drop across a small 0.1 ohm resistor, which I'm using to detect the current through the device. And then we have our second voltmeter over there, which is measuring the voltage at the source. And over here we've got the switch box, and we can see that as we switch in various values of resistance, we can vary the voltage at the source. So if we were to invert that, so negative 3.66 volts is effectively what we're applying to our gate. So as we can see in that picture, the more negative the gate voltage gets, the less current that passes through it, which is exactly what we're seeing here. So if we were to reduce some of that resistance, reduce our negative voltage effectively on the gate, we can see that our current increases. Now the way to read this one here, because it's the voltage drop in millivolts across a 0.1 ohm resistor, all I have to do is just move that decimal place 1 to the right, and I can just read that directly as milliamps. So that would be 2.7 milliamps for a VGS of 2.6 volts, or in other words minus 2.6 volts on the gate. Now by running through a series of those, you can build your transfer graph here. So on the vertical axis here we have current in milliamps, and down the bottom here we have our VGS in volts negative. And we can see here exactly what I did here. I put in a series of voltages or effective resistances to get me various more to the point voltages on the gate, and I could then plot how much current is passing through the device. And as we can see here that I was getting pinch off, in other words current was effectively falling to 0 at minus 3.5 volts, and then when I removed the voltage on that and then just very quickly applied VCC as not to overheat the device, which will vary the values, I could then quickly read off that I was getting 12 milliamps. So my IDSS, so with 0 volts on the gate, so flat out so to speak, I'm getting an IDSS of 12 milliamps, so which is the 2 values down here. So now I've effectively, in line with Woz's So again, with Wes's guidance or his recommendations, have now determined that transfer graph specifically for the device that I have. Right, so sort of moving on, I mentioned before that I didn't particularly want to, let me just turn that meter off so it doesn't beep later on. I didn't particularly want to go with this amplifier here because it's tuned, so it's a narrow band amplifier, and I was really after sort of playing around with the idea of a wide band amplifier that could, you know, ideally would be nice to sort of cover that 80 meters, 40 meters, and 20 meters at least would have been nice. And given that this was only going to get its gain by having tuned circuits, I decided to forego that, and I didn't actually build it up and have a play. What I did elect to do, and before I look at that, I'm just going to quickly cover a couple of formulas here. These are common formulas. So RS, that is the resistor that's in the source circuit there. So that resistor there effectively defines, in this type of configuration, what the voltage will be between the gate and the source. In order to work out RS, you use this formula here. So what you need to plug into it to work out what your RS is your pinch-off voltage, which we've now determined through test, ID, so the desired quiescent current through the device, and then brackets again, so that same quiescent current, in this case Idss on the bottom, which we know because we've also worked that out through test, -1. So by applying that formula there and plugging in our desired values and our known values, we can determine what our resistor needs to be in that source circuit. Conversely, our transconductance, our GM value there, is 2 times Idss over Vp, brackets 1 minus Vgs over Vp, which we can work out for our circuit once we've got it biased correctly with our known RS. Anyway, so just moving along, and we'll use those formulas in a sec. What I decided to play around with is another test amplifier that Wes had, which was used as a buffer amp, so a low noise buffer amp there. Not a huge amount of gain, but because we've got an input here leading into effectively an open circuit, because next to no current flows into a JFET. So effectively, if you're looking in this way, you just see, if we would take this away, a super high impedance, or resistance more the point. But by having a gate resistor here, we can have current passing through here. Sorry, my apologies. No current passing through here, which effectively pulls our gate to earth, which then allows us to have the voltage drop across our source resistor there, setting up that relationship that we saw in the previous circuit, where the gate is effectively more negative than the source, and our operation starts to kick in terms of regulating and regulating the current through the device. Anyway, so this is the circuit I decided to have a bit of a play around with. T1 is an FT37-34 with a 15:3 turns ratio to transform our 50 up, so 50 times our N, so 15 divided by 3 equals 5, 5 5s are 25, so therefore 50 times 25 equals 1250. So we're presenting to our drain at 1250 ohms. I elected to, just for test, to set the quiescent current through this device to be 6 milliamps, which was effectively half of Idss. So back to the graph we had here, just notionally set the quiescent current to be, like I say, halfway between pinch-off and our Idss, so sitting around here somewhere. And the thought there was that should give us the most linear range for variations of the input before we get to pinch-off or not. Anyway, so we talked before about, so in order to set our quiescent current at 6 milliamps, we need to determine what our source resistor is going to be. So using the formula we just saw before, we can plug in our values So VP from test was minus 3.5. We've got our desired 6 milliamps there. Under the square root we've got again our 6 milliamps divided by our IDSS, which was 12 milliamps, minus 1. Run that through, you come out with 170 ohms. So I'll use the nearest standard value of 180 ohms. I then sort of worked out on paper what the output, I think if I got the maths correctly, should be. And incidentally, it's not what actually came out in test, but I haven't actually looked at that any further. But my understanding is, in this particular case, this is the understanding. So a VN, we have a VN coming into the circuit here of 1 volt peak to peak, and we've got a effective load on the device of 1250 ohms. So that 50 ohms there being transformed through the turns ratio squared up into 1250 ohms. So those are the two knowns there. So an input of 1 volt peak to peak, a load of 1250. And we know from the JFET amplifier such as this that the current variation, or the current that gets passed now through this JFET here, is a function of the transconductance and that driving input voltage. So I signal equals GM times voltage in. So now we can substitute in to try and work out what that's going to be. So our GM is this formula we saw before. So just to recap, that's the one here, our value of GM. So now I'm just essentially plugging in our known values. So 2 times our IDSS divided by our pinch-off voltage, brackets 1 minus VGS. So the voltage between the gate and the source, I've just worked out to be that 6 milliamps quiescent current times 180 ohms. So that's the voltage drop across this resistor here, and then divided by our VP. Work that through, we'll come out with an I signal of 8.97 milliamps, and therefore V out, in other words the voltage across the primary of that transformer there, would be 8.97 milliamps. That voltage, that's again that current there, times 1250 equals 11.216 volts. Now that's not what we're seeing across the 50 ohm load. That's what's being dropped, or being created, wrong words, but we'll use that anyway, across the primary of that transformer there. So therefore we need to work out what is going to be on the secondary, and that's just simply the voltage of the primary divided by the turns ratio. Not the turns ratio squared. You only use the turns ratio squared for the impedance transformation. For current and voltage, it's just the turns ratios. In this particular case, it would be 11.26 divided by our turns ratio. So 15 turns on the primary, 3 turns on the secondary gives 5. So 11 divided by 5 equals 2.24. So that's what I was sort of half expecting to see across that 50 ohm load. So let's just quickly fire things up. So it's going to make a few little changes here, and then we'll just have a look what's going on. So we just need to transfer across our VCC. Just disconnect that. Make sure I get the right around so we don't let out the magic smoke. Come on. Of course my hands are a little bit crazy. Right, good. So we can see there on the scope the output, and we have on the SIGGEN up here, just slightly out of scope there, 12 megahertz at 1 volt, peak to peak. Interesting enough for a start, if we were to drop this, if we were to just see on the screen, and we can see that there, we can see it's pretty good in terms of gain across the HF spectrum. So we're now down to, what's that, 1 megahertz, and just climbing up there, that's 8, 9, 10, 11, 12, 15, 16, and then just starting to drop off now, which is, I'm pretty sure it's more, from what I can measure, a function of my signal generator than anything else, that it starts to drop off from that sort of 20 megahertz up to the maximum frequency of 24 megs. But suffice to say, if I could bring it back down to that sort of 14 megahertz, or the 20 meter band, and then drop that down to the 40 meter band, and then drop that down to the 80 meter band, it's pretty constant, so that's quite interesting. But interesting enough, when I actually worked out the voltage drop, which is this voltage drop here across the 50 ohm load resistor down here, which is that one just sitting here, I wasn't getting my expected 2.24 volts. I was actually getting half of that. I haven't really, to be honest with you, put too much thought into why that may be, which we can see there, that's 1 volt peak to peak. So I'm getting effectively 0 dB gain from the whole device. But one could argue, in terms of a buffer amp, having that high impedance on the input to reduce any loading on, say, an oscillator, then that's probably not such a bad thing, so long as, you know, from a gain distribution point of view, you were delivering sufficient gain out of this moving forward. I did have a bit of a play around with varying the turns ratio. So I went up from, I played around with 10 turns to 5 turns, then with a separate transformer on the output here, went down to 10 turns to 3 turns, and in all of those cases I was actually getting a reduced output. In other words, I was actually getting less than I was putting in, so I was acting more as an attenuator than an amplifier, so to speak. But yeah, so I'm not going to draw any conclusions from this video. It's just more having a bit of a play around, and I thought I'd sort of just pass on some of that information about determining the IDSS, so that zero gate voltage drain current, or the IDSS, and the voltage pinch off specifically for your particular device. Wes does say that if you're reasonably confident you've got a batch of devices from the same batch, so to speak, so you know it is a batched supply you've got, then you may be able to measure one and then have that across the whole batch. But you know, his advice was strongly to measure, like I say, the IDSS and the voltage, or the pinch-off voltage, specifically for each device before you go and actually build the circuit. So that was interesting, and like I say, I'm not going to draw any conclusions from that. It was just more of interest sake, just sort of playing around with that. I'm still thinking about what I want to do for an amplifier. If looking through the EMRFD and SSDRA, they certainly say that BJTs are equally good in terms of noise, being low noise amplifiers, if you treat them properly. So I think I might have a bit of a play around with some BJTs next. Look to dig out LT Spice and sort of go from there. But that may or may not be of use, this particular video, but you know, I found it quite interesting. It was certainly nice to do a bit of plotting there to work out those values. Yeah, I'll leave it there, 73s, and we'll keep tinkering around and playing at this end. Cheers all.